Our project this semester is adding Xen VTPM support to OpenStack. My name is Daniel Pereira, and my partners are Tony Cow, Nick Morrison, and Gerardo Rago. Our mentor is Nabil Shir, working at Lincoln Labs at MIT. Just a little cloud computing humor to lighten the mood for this presentation. So our project goals. This is our user story. As an OpenStack user, I want to provision TPM resources so that I can verify the integrity of my host. I'm going to break down each piece of this user story. So first, as an OpenStack user, the primary concern is the creation and management of virtual machine instances. This virtual machine is essentially a computer built from virtual hardware. Virtual hardware that represents computing components. As you can see, there's some pieces of it down there. The next piece, I want to provision TPM resources. So the TPM is a physical piece of computer hardware, as you can see on the left. We want to virtualize this TPM. TPM stands for Trusted Platform Module, and it's basically an 8081 microprocessor with cryptographic hardware, some NVRAM for secure storage, and a factory-programmed private key, known as the endorsement key, or EK. This is an asymmetric key pair whose private portion is burned into the TPM during production and only accessible to the microcontroller unit. This endorsement key can be used to sign data coming out of the TPM, and we must assume that solely the TPM is capable of creating these signatures. And the final piece, as an OpenStack user, I want to provision TPM resources so that I can verify the integrity of my host. Why would this be useful? Currently, tenants have limited ability to verify the underlying platform to which they are deploying. We can utilize the TPM as a hardware root of trust. On the TPM, there is an array of platform configuration registers, PCRs. These are stored as SHA-1 hashes representing the runtime state of the host at various stages of the boot sequence. If something changes in the boot sequence, the PCRs will reflect that change. For example, with a known set of PCR values, we could quickly determine whether a rootkit was installed. With access to the TPM, a user can both verify the integrity of their host and link that host to a specific physical server. Our mentor Nabil has already done some incredible work on trusted computing in the cloud with a system known as Keylime. Keylime handles the work of verifying the integrity of hosts and instances using TPMs. With this system, a cloud user will know if their host failed the TPM root integrity check and can then deny that instance access to further security services. Thus, even with a compromised hypervisor, an attacker will not be able to gain access to the cloud user's infrastructure. Our portion of the project is to automate the creation of VTPMs, making them available to the user instance for use with technologies like Keylime. We are implementing this stack, the Nova Libvirt libxl stack. Currently, neither Nova nor the underlying Libvirt layer has a notion of Xen VTPMs. Only the Xen layer could recognize these VTPMs. So first, we define a new device on Libvirt for VTPMs, and then propagate the intent to create a VTPM to the libxl configuration at spawn. Then, on the Nova layer, we provision the necessary resources for a VTPM stub, and spawned it using the semantics we defined in Libvirt. This is simply a small disk image and UUID requested from the Xen VTPM manager. We then augmented the compute instance's configuration to attach a VTPM to it. With these changes, we can now execute Nova boot, and a new instance will be created with a VTPM attached to it. Upon deletion of the instance, the accompanying VTPM and associated resources will be destroyed. Now, Gerardo will give a demonstration of some of the features of our project.
The purpose of this quick demonstration is to show that we are in fact running OpenStack on our Xen host using DevStack. I'll be showing you guys the administration panel for Horizon on our host. Over here on Chrome, I have moc01.bu.edu, which is a subdomain given to us by the MOC, and I'll be logging in as the administrator. As you can see, we're in the admin dashboard. The only thing I wanted to point out here is if I go to hypervisors, you can see our Xen host here, and the type of the hypervisor is Xen and not QEMU. And here's some real resource caps on that machine. Also see the Nova Compute host, and that's it. I will now demonstrate how we are able to provision VTPM resources using Nova Compute Service. The goals here are to first create an instance with Nova Boot, show that we have provisioned a VTPM, highlight the various layers of abstraction, and then delete the instance and tidy up. So over here, I have a shell with valid keystone credentials for OpenStack, and I will be performing Nova Boots to create a test image called VTPM demo. As you can see, it has now just spawned it, blah blah blah. At this point, our VM has been spawned, and we can see on the Nova layer that we have a new VM here, and it's active and running. Similarly, on the Birch layer, we can see that that domain has been created here called instance, and also a corresponding domain called VTPM, which is used by instance. On the Xen layer, we can also list, and we can see our complete Nova Compute stack here, which including domain 0, VTPM manager, our keyline VM, and its privileged VTPM. Also the two domains created by Nova that we saw in Birch. In this directory, we can also see the VTPM image that we created from Nova that backs the VTPM. Now, to clean up, all we have to do is do a Nova delete VTPM tests, or demo. And after this command, all the resources should be freed and the domains should be gone from every single layer. There, now it's gone. And if we do sudo xl list, see that the domains are gone there, and also on the Nova layer, the VTPM domain has been destroyed. This is our UUID REST server demonstration. The goals here are to request a VTPM UUID from the VTPM manager, and then return it as a JSON object to Nova. So first, I have here a shell on our keyline VM running the UUID server, and over here, I have a shell on domain 0 where Nova lives that will request a UUID. So as you can see here, we get the UUID here, starts with 697C, and on this side we can see that same UUID from some logging from the VTPM manager, and we also register that on our keyline platform. So what did we learn about in pursuing this project? Basically, we learned a lot about developing software for the cloud. And the first major revelation I wanted to go over was using the cloud itself as a development tool. The idea that we had all these cheap disposable computers was very powerful because it let us do all these destructive operations such as installing DevStack without worrying about the time and money cost of replacing a computer. The other important idea was that we also had all these snapshots of known good setups that we can always roll back to or spin up on multiple VMs. We learned a lot about OpenStack development using DevStack. Now, as we've demonstrated previously, DevStack is a very powerful piece of software that allows you to deploy the entirety of OpenStack from source on a single machine. Over here on the right, I have a console, and you can see all the various OpenStack services here and there's source code, which you can modify and deploy in a matter of seconds. As part of developing with DevStack, we also learned how to debug OpenStack using PDB. Here, I've added a breakpoint right before we create a VTPM. And over here, I have a shell in which I've triggered that breakpoint, and I'm going to now connect to the screen session containing that trace. Here I have an interactive PDB session where I can examine variables such as the VTPM UUID, look at the stack, check the arguments to the function, and basically execute any Python command that would help me determine the root cause of any bugs. Early on in our project, we learned how to run OpenStack unit tests using Tox automation. What's nice about these unit tests is that they offer nearly complete coverage of the OpenStack codebase. On the downside, it does take about 10 to 20 minutes for them to run to their entirety for just one OpenStack service. So over here on the right, I've shown running the OpenStack style checker and watching our code fail the unit test.
Now I will speak about limitations and future work of our project. So the first limitation of our implementation is reproducibility. The nature of our project is such that we have made many small configuration changes across a multitude of platforms that we are using. In addition, some shortcuts were made to allow our system to be in working order. As it is, our system is not production ready, and as such will be likely hard for another group to reproduce with the same results. Specifically, looking at our changes in Nova, we see where some of our complications lie in terms of our code not being production ready. For instance, we are not yet able to track resource consumption for the VTPMs, so we are not able to provision them appropriately based on the available resources. Also, our method of fetching UUIDs depends on our native API as well as our client software keylime, which is not publicly available as of yet. Other shortcuts such as hard-coded paths and names and a lack of error handling of failures contribute to this code not yet being production ready. Looking to the future, we hope that this code will be able to be pushed upstream. Our changes to Libvirt are the most likely candidates to be pushed up with little complications. As it is, it could be immediately useful to the community. As mentioned before, the changes to Nova will require some work before they are ready to be pushed upstream. They are also dependent on the successful push of Libvirt changes. Overall, with some cleaning up, we hope our code can be pushed out to the open source community and become an essential piece of trusted computing in the cloud, allowing users to simply provision trusted VMs without dealing with all of the messy details which have complicated this project.